Okay, in a circuit, you can have a combination of both series and parallel in a single circuit. Such is referred to as a mixed resistor network. In resolving a mixed resistor network, the following steps can be employed. All right. The first one is to identify and label. So mark all the resistors with a reference R1, R2. You can say RA, RB, RC till RN. All right. But any notation you are using, just stay consistent with it. Okay, identify the two terminals between which you need to take the resistance, the total resistance. Here, this example that we had, we took um resistance between these two terminals. Let's call this terminal A, terminal B. So it was easy for us because we're dealing with parallel. We know these are in parallel, all right? So in a mixed network, you can have parallel, you can have series within two terminals. So you have to now identify, first of all, you label them, and then you now identify the all the resistors that are in parallel. Find resistors that share the same two nodes. All right, these are in parallel. I beg your pardon. Combine them into a single equivalent resistor. Now, what we are saying here is that when you look at your circuit, first of all, identify the points between which you want to take your total resistance. Identify all the parallel combination in the circuit. Identify all the series combination in the circuit. All right. Use the principle for parallel combination to reduce the parallel resistors, and then use the principle for series combination to reduce the series resistors. By the time you follow that steps one after the other, and then you keep redrawing your circuit, you will end up having your total resistance with ease. So a simple flow chart that describes this process is given here. Step one is you have your original circuit. Step two, you find the parallel groups, that is the resistors in parallel. Step three, you combine the parallel resistors. And then step four, you find the series resistors. And then step five, you add the series resistor. And then at the end of the day, you are now left with just a single resistor. But the caveat here is that when you are trying to resolve a parallel combination within the circuit and you come across a series, you deal with a series. In the same way, when you are trying to resolve a series combination and there's a parallel combination interfering it, you deal with the parallel combination. Okay, let's take this example or this explanation. Here is a case where there's a circuit that has a combination of both series and parallel resistors. This is the example we're having here. All right, for purpose of illustration and explanation, you can see this whole network of resistors. All right, here we want to take the resistance between 2 points. Let's call this point A, and then let's call this point B. So whenever you have this kind of combination, your circuit might not necessarily come in this form. Any format which your circuit comes, just try to identify your series and your parallel, all right, within the circuit, and also identify the points between which you want to take your total resistance. So here, you can see that you have these resistors here. So to solve a problem like this, we follow these steps systematically. Number one, identify the pair of nodes between which we want to find the equivalent resistance. All right. So we have a method for trying to find equivalent resistances without having to resort to a messy combination of Kirchhoff's laws. All right. So I believe you did Kirchhoff's laws, Kirchhoff's current laws, Kirchhoff's voltage laws, Thevenin's theorem, Norton's theorem in a previous course before now. So, but here we just want to emphasize how to easily resolve a complex resistive network that comprises of both parallel and series combinations. All right. So the first one is identify the terminals. Here we have identified the terminals. All right. The next step is starting at the opposite end of the network. Identify series and parallel combination that can be reduced using simple formulas. So if you have identified the points between which you want to take your resistance, total resistance, you start resolving from the other end. You don't start from this end. All right. So this is the point between which we want to calculate our resistor. So we'll start resolving from the other end. And the first thing to do is that from this other end, we try to identify series or parallel combination, and then we reduce them gradually until we get to this first resistor. All right. So starting from this end now, let's identify if there's a series or there's a parallel combination. So from this end now, we have R4, we have R3, we have R5. These three resistors, they are in series because any current that enters this place, the same current is going to flow through them. If you look at it very carefully, whether the current is coming from this angle, all right, if the current enters here, I, it will go like this, it will go like this. So there's no other path that can divert the current from any of the resistors. So any current that enters either through this way or through this way, the same current is going to flow through them. So it means that these three resistors, since they are going to be carrying the same current, they are in series. So we spot them like this. So if they are in series, we reduce them using the series formula, all right, which is going to be equal to R3 plus R4 plus R5. So whatever we get from this process now will give us the equivalent resistance here, all right. So we can call that R345. That is the total resistance for 345 because they are in series. So by the time you reduce that, you're going to have a single resistance value now, which is the resultant of these three resistance values that has been resolved in series. So you now have it here. So you now have R345 as the resultant of this. So you have dealt with the first series combination that is encountered. If it is parallel that is encountered first, you deal with the parallel. All right. So you are now left with this total resist series combination and this one now. So you continue the resolution again. You still keep looking from the other end. In this case now, whatever you have here is in parallel with this. So you now use the parallel formula to combine this. So by the time you use parallel formula to combine this, you will end up with a single resistor again. All right. So the parallel combination here now we can say this is a 1 over R2 plus 1 over R 345 345 will give you the total resistance you want to get there, RT. Let's just call that 1 over R just for purpose of illustration. So but what we are saying here is that this and this are now in parallel. So you have to use the parallel approach to resolve them. So when you resolve them, you now have the total resistance R2345. This is just simply saying that this total resistance now is a consequence at this level here because we are still having R1 there. At this level, the total resistance so far is a consequence of all this resistor. R2, R3, R4, and R5. And we started by identifying the ones in series and dealing with them. And then going to the next phase, we have parallel, deal with them. So far, we have identified, we have resolved 2, 3, 4, 5, and we have this value. So we continue. If we continue, we're going to be having this now is going to be in series with this because any current that is coming in from here now is going to follow here. All right. So this and this are in series. So at the end of the day, we just add it up. R1 plus R2345 gives us the equivalent resistance. So it is simple to deal with equivalent resistance in a complex resistive network if you are able to first of all identify the terminals between which you want to take your resistance, one, and then two, begin to resolve from the other end by dealing stepwise with any series combination you come across or any parallel combination that you come across until you attain to the final resistance value. Okay, let's look at this example here. We have this resistive network, all right, and the question says find the equivalent resistance looking into the indicated port of the ladder network shown. Okay, so this is the ladder network. This is like a ladder network, a combination of resistors in series and in parallel. And this is the direction which we are considering to take our resistance from, like between, I beg your pardon. So let's call this X, let's call this Y. So following the rule, we are looking into the networking from this direction. In resolving the resistance, we begin from the opposite direction, from the other end. According to this step, identify the pair of nodes, then starting at the opposite end of the network, identify the series and parallel combination. So if we do that, you can see that we have R6 from this end, we have R6, we have R5. They are in series because the same current is going to flow through them. All right. So we start at the far end. Starting at the far end, we see that R5 and R6 are in series. All right. So they are in series. So we simply add them up. All right. When we add them up, 330 plus 680 gives us 1010 ohms. So we have been able to deal with this. All right. So this has been dealt with into a single, you know, resistance value. And that's what we're having here now. So that single resistance value now is what we're now having here in this manner. Are we together? So representing resistance from 5 and 6, R5, 6. So we still continue the journey. All right. We've reduced this. We keep going into the circuit from the other end. So this R5, 6 plus R4 now are now in parallel. So we'll now use the parallel formula to also deal with this. All right. So we now have to deal with this using the parallel formula because they are in parallel. Why? Because any current entering, you know, this point will divide here and here. The same current cannot flow through them. All right. So R4 is in parallel with R56, which is what I've just explained. So we'll now use the parallel combination approach to resolve this. All right, which will give us R456. That means the resistance resulting from this combination. If we do that, we're going to be having 1 all over, all right, 1 all over R456 is equal to 1 over 1010 plus 1 over 680. All right, we are resolving this and this in parallel. So by the time you do the calculations, all right, and you simplify, you're going to arrive at 407 ohms. So that means this entire issue here now, this parallel combination here has been reduced to 407 ohms, which is what we're having here. Okay, so we continue like that. We still continue moving into the network. We continue moving. So you can see that here now we now have 407 ohms is now in series with 330 ohms, because if current is coming through this place, the same current is going to flow through this place. If current is coming through this place, the same current is going to flow through this place. So whichever way current is coming, the same current will flow through both of them. So they are now in series. So we now resolve this in series again. This 330, okay, this 330 plus 407 will now be resolved in series by simply adding them up. So we have R3 plus R456 are now in series, which I've just explained. By the time you add it up, you're going to be having 407, all right, plus 330, all right. 407 plus 330 will give you 1010 ohms. This 1010 ohms is just like a coincidence with this first value we got. It doesn't mean that you always fall back the first value. It depends on the values of the resistors you are resolving. So for here, this gives us 1010 ohms, all right. So having gotten that 1010 ohms, we still continue. All right. So step 4, R2 will now be in parallel, because what you have here now is I beg your pardon, let's correct this very well. So I see there's a mistake here. Okay, so this is not correct. This is 737. Let's correct that. There's a mistake here. So by the time you add this and this, you're going to be having 737 ohms. which is what we're having here. All right, 737 ohms. So that was a mistake. Let's also verify this. Okay, let's verify this value again and be sure that it's 407. Okay, this times this divided by this times this. That should be 407, but we can verify, all right? Verify with your calculator. Okay, so this is 737. So this 737 is now in parallel with this. You apply the parallel principle again to resolve this, all right? And then you proceed. By the time you do that, you're going to be having 354. Okay, but ensure you verify all these values with your calculator. The purpose of this slide is just to illustrate how to reduce the circuit, all right? And at this stage, you now have it finally that you have 330, you know, in series with 354, right? And then you simply add it up to arrive at this total resistance value. So do well to verify these values, these figures again with your calculator as you take it step by step. So this is how to resolve, you know, a complex resistive network, right? Where you have a mixture of both series and then parallel combination. Okay, we have a simple example here. All right, I'm going to solve the first part of the example, and then um, you can try your hands on the second part of the example. Okay, the question says find the circuit for the circuit shown below. I beg your pardon. Determine the equivalent resistance as seen by the source. Find the currents I1 and I2. So you want to find this current, you want to find this current, you want to find the equivalent resistance. So equivalent resistance as seen by the source, that means we are looking into the circuit from this direction. All right. This is where we are looking into the circuit from this direction. So when we are trying to find the equivalent resistance, we'll first of all assume that this battery is not there. And then we'll look into the circuit. So by the time we do that, let's mark that. Let's just put this line. Just put something like this. Um, something like this. Okay, so let's call this X and Y. Let's call this X and Y. So we are looking into the circuit from this direction, just like we have here. All right, this direction. So when you're looking to the circuit, you just assume that this 6 volt is not there yet, since you want to resolve the resistance. By the time you finish resolving the resistance, you can now bring in your 6 volts. Okay, so we'll begin from this end. We can see that, let's label our resistors for ease. So let's call this R1, let's call this R2, let's call this R3, and let's call this R4. Okay, R4. So we'll begin from this end, we resolve this way. Beginning from this end now, you can see that R3 and R4 are going to be in series. The same current is going to flow through them. All right. So dealing with this portion of the circuit now, we have it that R34 now. Let's just say let's call that R34. R34 is going to be equal to R3 plus R4, right? Because they are in series, and that's going to give us 4 plus 2 will give us 6 ohms. 6 ohms. By the time you look at this circuit now, this can be represented with a 6 ohms. Whatever you have gotten here will now be in parallel with this, will also be in parallel with this. Okay, so if I reduce this circuit properly now, I can have it as, first of all, I have something like this in this manner, and then here, beg your pardon, You just take this in this manner for illustration. Beg your pardon. Let's just draw that properly. Okay. So remember, this is the direction we are looking at the circuit from. This is our X and Y. Okay. So we have been able to resolve this last series combination here, and this is 6 ohms now. We are now left with these other ones, R3. Okay, this is R3. Okay, so this is now R3, and then we also have R1 here, R1, R1. Okay, so this is R1, this is R3, and then this is R4, 5, R3. I beg your pardon, R1, R3. Oh my God, there's a mistake here. Pardon me for that. Let's call this R2. Let's call this R2. This is supposed to be R2. So this is R2. This is R2. Sorry about that mistake. This is R3 now. Yeah, that is correct. That's correct. So this one is for R34, R34, which we have done. So you can see that every other thing we have left now are in parallel. In parallel. So you just apply the parallel combination here to get the equivalent resistance. Okay. So you're going to do this as an assignment. You're going to tell me the equivalent resistance, and then you are also going to calculate the currents I1 and I2, and get your answers ready. You'll be told when to submit and how to submit the assignment.